We're doing a quick little overview of Cayley tables, a nice way to organize binary operations. You put your A on this column, all the elements of A, let's say you had 1, 2, 3, 4, and all the elements of B go here. A star B goes in there. And you might say, well, that's boring and not very difficult. If you do an operation like A star B that you see here, you can see how we filled this in. We notice that there's some pieces to the table that give us information that we couldn't see before. One is that when you lay these out, if all the elements are present from 0, 1, 2, and 3, if only 0, 1, 2, and 3 are shown, then we'd say it's closed. But this one actually is not closed because you get things like 4 and 18 and 12. It's not commutative because if you show the diagonal here, each symmetric term should be identical if it's commutative, and this one's not even close to being commutative. For the Latin square, all we're looking for is rows and columns have different, they all have the same members, they're just all mixed up. For the rows and columns that you see here, 1, 2, 3, similar to your Sudoku puzzle, 1 through 9. We're working on number 1, which says layout 1, 2, 3, 4, and then do the module 5. So you're going to divide by 5 and look at what the remainders are. So what did you get for the first row, Vishal? What did you get for the first row here? Going across here. 1 times 1 is? Yeah, not very interesting, this first one. And by the way, you can do the same thing down here to save time, right? And then 2 times 2 is 4. Then what will 2 times 3 be? Mod 5 is going to be 1, right? Because 6 divided by 5 will have a remainder of 1. How about 2 times 8? What will that have? 3. Now, what do you notice about 1, 2, 3, 4 and 2, 4, 1, 3? And it looks like it's going to be close. Well, let's keep going. 3 times 2 is 6. 3 times 3 is 9. 4 times 3 is 12. Keep going. 4 times 2 is 8. 4 times 3 is 12. And 4 times 4 is 16, which is 1. So is this closed? Mm-hmm. Tell me, is it symmetric? Is it? Yeah. That's something? Love it. So that is, if it's symmetric about the diagonal, yeah, it is going to be commutative since symmetric about diagonal. Great. All right, now, what they're saying is 2 times what is going to give you 1. Remember when we had to do this with the modular math back in number theory time? And we had to deal, and it was kind of complicated, and I said, someday it's going to get easier. Today is not, today is that day. So what you do is 2 times what will give you a remainder of 1. So what could you do to solve for that? Well, you start with a 2, and then do we multiply by 1? No, you look for the remainder. And so 2 with the remainder of 1 is going to be what? 3. So x is going to be equal to 3. Does that make sense? Look how easy that is with the table. How about this one? 4 times what is going to give you a remainder of 3? X is what? So you're going to go here, you're going to go 4, you're going to have a remainder of 3, so you would multiply 2 by that. And that makes sense, because 4 times 2 is 8. That will give you a remainder of 3. That's cool. You got it. 3, is this x equal 3 again? Is that right? Mm-hmm. And what will this one be? Yeah. So you just go 4x equals 1, so that's going to be what? X equal 2? 4. There you go. State the identity if it exists. So we're going to look at the identity. Now they say in the book, well, it's obviously 1, but if you do 1, 1, and you get 1, the identity is going to be 1. I don't think the book explains that real well, but I think what you would do is you would say, think of it this way, if you went A star E and you get A, right? A star E and you get A. So A giving you 1 will be 1. 2, look at this. 1, and you to get 1 as the remainder, you would have to have 1 up here. How about 2? To get 2, what would it be? To get 3, what would it be? So do you see why it's obviously the identity?
So this A star E has to equal to A, right?
A star E equals A, yeah.
Yeah, so 2 star 1 equals 3, though.
2 star 1 equals 3. Yes.
Yeah, that's not true.
Well, here, we're going to come back to that. When we're looking at the inverse, we're actually looking at that right here. So the 3 inverse is equal to 2. What we're saying there is 3x is equal to 2. So 3 to give you 2, 3, 2, what would the inverse be? Oh, just a quick mistake there. Remember, it's the inverse. So 3, you want to get the identity, right? To inverse. So let's talk this over one more time. A star E equals A, right? So what's E equal to? A star what? A inverse, right? That's what the inverse is. So 3 inverse, we're going to show that it's equal to 2. So 3 what is going to give me 1? 3 what is going to get me 1? X is equal to 2. So what you would do, here's how I would do it. Here's what I would do. I would go all the ways that you get 1. 1 star 1 equals 1. Any other ways to get 1? 2 star what gives you 1? 3, yep. Any other ways? 3 star 2 and 4 star, yep. 3 star 2, 4 star 4 gives you 1. So what the way the book describes it, and I thought this was a little confusing, but I'm going to do my best. They're saying that 1 and 4 are their own inverses. Okay? 2 and 3 are what? Are inverses of each other. Would you write that down, please? So when we get the combos to get the 1, we found the identity by saying A star E equals A. So whatever got me this is going to get you your E. This is the 1. Gets itself. These are pairs. So then it's going to be that. And then we won't always have an identity. Sometimes we will. and then you use that and see where you get that value of 1, and that's how we found those 4. Go to 2 is excellent. Let you play around with that one a little bit on your own, but let's zip on down to 3. I want you to end with 3. If you can do 3, you got this down. 2 is good review. It says the universe of this set is 1i, -1, -i. Set up the Cayley table and see if you can answer most of these. First of all, how are we doing here? Did you get 1i, -i, -1? I like to do these. By the way, because these are the same, what's the identity going to be? Yes. It's going to be 1 because these are all the same. Then the inverse we'll get to, but let's finish off the table. So I times I was -1. I times -i is what? It is 1. Kind of weird. I times -1 is going to be -i. Negative I times this is 1. I times -i is -1. And I times -1 is I. Then the -1, I, and 1. Okay. So now the only other thing we have to do is we do need to show commutativity. Is this commutative?
Yeah.
Yes. So you could say commutative. It is symmetric about diagonal, therefore commutative. All right. Associative. Just watch this. Let's do I. The inverse is going to be 1. What else? I and -i are going to be, and also -1 and -1. So 1 and -1 are themselves. I and -i are together inverses. Have a great day. Test tomorrow. Hey, normally you can't come in Friday morning, but for you guys, you can come in tomorrow if you have questions, because it's a test day. 1500.